sinusoid shape is the result of the sine function of the angle. And the angle has components such as frequency and phase. So here is a carrier signal and some modulating intelligence. What views could those be? Oscilloscope view or spectrum analyzer view?
Yep,
No, they are oscilloscope because they are in time. Along the horizontal axis runs the time. So this is the time domain display of the carrier and the modulating intelligence. And see how the amplitude of the intelligence, when it does swing in the positive direction, it would increase the time period of the carrier wave, therefore it reduces its frequency. It deviates the frequency, that's the buzzword. And when the intelligence does swing in the negative direction, it also deviates the carrier in the other direction, it increases its frequency. So a frequency modulated carrier does have a deviation. For a few examples, 99.5, the local FM radio station, deviates plus minus 75 kilohertz. The local CTV television station that has a frequency modulated voice channel only deviates plus minus 25 kilohertz. Then any of the FM services such as taxi cabs or police is not using FM anymore, they used to deviate by 12 kilohertz. And all the way down to ham radio equipment, where your handheld walkie-talkie deviates by 5 kilohertz only. Nevertheless, the carrier is deviated away from its resting value. That's a frequency modulated signal. What we see here is a spectrum analyzer display. This actual picture was captured by myself when I was teaching at Sud College, because at Sud College they have a spectrum analyzer by Signal Hunt. You can have one, it costs $1,200. So it's about costs the same as a low-end HF ham radio. And the spectrum analyzer like this, I did love this because live in the middle of a lecture, I could produce an FM, a spectrum, and put it on the wall like this and change the parameters from the oscillator. So this was actually captured at Sud College. This is the frequency spectrum of an FM carrier deviated up and down. And again, this is something you can have for much less. This can be achieved with a software-defined radio, which we will talk about that Thursday. But right now, I am just pointing out that a display like this, there's this top part, which is called the waterfall display. And underneath there is the spectral deviation, and this equipment is really available for ham, so you can test your 2-meter band FM handy talkie with some equipment which I will bring around and show you Thursday. Now we talk about transmitters, and let me read this quickly. A ham radio transmitter must accomplish a number of goals, such as to generate a radio frequency carrier at a specified frequency, free of distortion without any drift. Drift would mean that you tune up your radio receiver and the transmitted signal you are monitoring would just move away, would drift away. A ham radio transmitter must be able to modulate the carrier according to the type of intelligence used, which could be CW from Morse key, it could be voice or microphone to produce amplitude or frequency modulation, single sideband, or there's a new one here coming, digital modes. What digital modes are many, And the latest one, they start with your computer. For you, the operator, you would type something on the keyboard, and that would go through the sound card of your computer into the microphone input of your radio. It would be simulated voice, and at the receiving end, somebody would tap the speaker of his receiver and feed that signal into the sound card, and his computer would have a replica of the text. That is called the digital mode. Control the transmitted power between the range allowed by Industry Canada. Of course, we are a hobby very well regulated. There's a range of power we are licensed for. There's provision to be keyed up for transmit and keyed on during receive. So a voice transmitter is keyed up when you push to talk. You don't have to talk yet, you just push. And you keyed up your radio, you power your stages, and your radio is ready to transmit. Should not interfere with other services or other ham bands. The other services, well, the biggest complaint about the ham radio hobby is people's television receivers in the neighborhood. If you interfere with somebody else's television receiver, never mind if it's not your fault, because most of the time the ham radio equipment is built really to military standards and it's perfectly set up, and somebody has a leaky, badly tuned old television receiver that picks up anything, electric meters, noise from the spark gap of cars, and you all want to blame it on you, the ham radio operators. So this is an ever-going issue we will have with other services. The ham radio has an operator interface. Well, now the operator interface in the past was switches, dials, cranks, and all mechanical components, which tend to be expensive nowadays. So nowadays, a ham radio is having a different kind of operator interface, mainly push buttons that they bring up menus, computer-like menus, and you have to navigate through and you'll get lost in those menus. A modern ham radio transmitter needs really some time from the operator to learn it, to navigate through those menus. Ham radio transmitter is matched to a 50 ohm output impedance. Well, there is actually no law against using antennas with any other impedance. It's just the ham radio, as it comes out of the factory, it's always comes with a 50 ohms output impedance. So if you are using an antenna that is not 50 ohms, which we are using such antennas, dipoles and wire antennas, then we have a whole extra added unit in our setup called the antenna tuner, what makes our 50 ohm radio to be able to cooperate with, say, a 600 ohm wire. And finally, it must be safe to operate, because sometimes we use tube amplifiers and there could be high voltage, 1000 volts on the plates. Safe to operate. The block diagram of a CW transmitter coming up. This is a figure that is in your textbook. I did just took the trouble to enter it into my word processor and color it up, but that's the same layout. And the CW transmitter starts with a master oscillator. This master oscillator is a sinusoidal oscillator. Elsewhere, it may be called a variable frequency oscillator or a VFO. So a CW transmitter, more often, it's tunable for all different bands and within the band. But here what's illustrated in your textbook is just a fixed frequency transmitter, the master oscillator. The master oscillator is followed by a driver buffer stage. Where there is an oscillator, the oscillator needs to be sheltered because the oscillator must have a very good frequency stability. And if the loading of the oscillator changes, just imagine that you are idling at a traffic sign at red, and your car engine is running idle speed. And then the light turns green and you switch it into gear, then the RPM drops. So you have to put power to it. So the frequency or the rate at which your shaft turns is a function of loading. So a buffer stage would provide steady, constant amount of loading to the oscillator, no matter what you do later. The power amplifier has a gain control dial. You can turn the power up, down, but the master oscillator would not take knowledge of this because it has a steady load, always the same. And that's what the buffer amplifier is doing, to shelter the oscillator, to keep it on the same frequency. The stages of this transmitter are obviously powered by the same power supply. And then finally we have a telegraph key which you push and then you transmit into an antenna. There is one of you finding that must. So this is really simple, the block diagram of a CW transmitter. The master oscillator itself, very often it's a phase-logged loop. Now, the key component of the phase-logged loop is a phase detector. A phase detector is a unit when it is getting the same thing over its two inputs, then the phase detector does not complain, does not produce an error. But when one input or the other is different, and the two inputs are different from each other, the phase detector would output an error signal. This error signal is changing in step with how much difference is between the two signals. So we take here to keep the difference non-existent. For an example, here is this voltage-controlled oscillator. Well, most laboratory oscillators are voltage controlled, and they have a dial, and you turn the dial up and down to change the frequency. Really, you turn a potentiometer, you apply a voltage to an oscillator. So this oscillator is running, say, on 10 megahertz. Then the 10 megahertz is divided down by a divide by 10 frequency divider, so 1 megahertz comes out. Here we have a 1 megahertz crystal oscillator. So the 1 megahertz and the 1 megahertz, they match. So there is no error. But for some reason, your output wanders up by a kilohertz. So suddenly, a kilohertz up, when you divide it by the divide by 10, 1000 by 10 is 100. So your 1 megahertz reference would see a signal feedback which is 100 hertz off. So suddenly the phase detector said, hey, you guys are not on the same page. One of you is off. So you have to put out an error signal. And that error signal, after some filtering, would tell the voltage controlled oscillator, would you please kindly go back to where you were before because you wandered up. So this is an automatic frequency control system. And most ham radios, they have this. Except many new ham radios, they now have a direct digital synthesizer. I will just describe that to you, but to understand this well, you need to have some good advanced computer technology knowledge. In digital electronics, there is something we call a lookup table. So you draw a very nice sine wave, and the sine wave has instantaneous values. And so you approximate that sine wave with a staircase waveform. Suppose 256 different steps. Well, 256 happen to be 2 to the 8th power. So we are talking about an 8-bit code in a microprocessor. So if the sine wave is approximated with 256 stair steps, each stair step has its analog voltage value. And that value fed through an analog to digital converter would produce an 8-bit code. So all of those 256 different 8-bit codes, from 0, 0, 0, 0, 0, 0, 0, 0, that was 8 zeros, all the way to 1, 1, 1, 1, 1, 1, 1, 1. All of those values are in a lookup table. So a microprocessor that has a start pointer feature that the program is running and would point to different entries in that lookup table. You just read out the 8-bit code for the sine wave, feed it back to a digital to analog converter, and then you just synthesize the sound wave approximated by 256 stair steps. You want a higher resolution, you go to 12 bits, 14 bits, that's how the integrated circuit direct digital synthesizers work. So what's a direct digital synthesizer? It's a large lookup table where small instantaneous value changes are converted to 12-bit code, and those code values are being read out by the programming of the microprocessor, fed through a digital to analog converter, and a very small stair step approximation of the sine wave will come out. Those little stair steps are so tiny that when you see it on the oscilloscope, the width of the beam, the width of the electron spot is larger than several closed stair steps. Here you would see it as an absolutely smooth, like my ham radio is a Yaesu FT840, something like a 20 years old. It's still good, it's doing the job. Ham radio, it has a direct digital synthesizer in it. So the direct digital synthesizer is based on modern numerical control and digital technology. And the phase lock loop is more like its predecessor. It's based on mainly analog technology. Both are extremely widely used in ham radio to generate the sinusoidal carrier wave. An AM transmitter and its block diagram, again, by those page numbers, you will find them in your textbook. Now with the same oscillator, we make a point that we want to tune this radio, so we call it variable frequency oscillator. Again, it has a buffer. What would that buffer do? It helped it maintain its stability by providing a fixed load, and the loading of the stages that follow are not going to influence the frequency stability. Now we introduce a new block here called a frequency multiplier. The frequency multiplier is an electronic block that can change the frequency of an oscillation by an integer value. 2 times 3 times 4 times 5 times. There is no such thing as a fractional frequency multiplier. It's always like an integer value. This is based on a very, very old mathematical theory developed by Joseph Fourier, who was a good friend of Napoleon Bonaparte. Was with him in Egypt. Napoleon made him the governor of Egypt. And then after they were pushed out from Egypt, Napoleon made Fourier in charge of paving the roads in the Grenoble area. I know all this because I went back 2 times to this Alps to ski downhill there, out of Grenoble up. So I walked on a cobblestone laid by Fourier. This guy Fourier had time at hand when he was in charge of paving the roads, and he developed a theory according to which every single oscillation that exists could be decomposed into an infinite number of absolutely pure sinusoidal components. And those components are called the harmonics. The lowest frequency one is the fundamental. Say a 1 megahertz square wave would have only odd harmonics of 3 megahertz, 5 megahertz, 7 megahertz, 9, 11, and so on. If a sinusoid is changed any which way, it's pressed together to be a narrow pulse. Even harmonics appear. If you cut the top, if you chop the top of a sine wave, it starts looking as a square wave, so odd harmonics would appear. So there are even an odd harmonics. And a frequency multiplier would distort the sine wave in a fashion either by making it narrower like a pulse to generate even harmonics, or by clipping the top to make it look like a square wave to generate odd harmonics. So you could run a VFO on 7 megahertz, followed it by a frequency multiplier by 3, called a tripler. So then you would get 21 megahertz. So
the purpose of increasing that is to do what?
Just to do a new handband, because you have a 21 megahertz handband. But you can start right away with the 21 megahertz oscillator, but you lower the frequency of the oscillator, the more stable it is. So you get a more stable oscillator by tripling and quadrupling the frequency of it, rather than run it right up high. And anyways, if your ham radio needs 7 megahertz, then you use a 21 megahertz crystal to have the 21 megahertz. Then how do you go back down to 7 megahertz? So most ham radio equipment, they generate oscillations for the lowest ham radio band, and those ham radio bands, they are all integer multiples of each other. So that's what the frequency multiplier is doing. A power amplifier looks like this. If you have a VHF radio, your vehicle, a mobile radio, you can usually see this at the back of the radio. There's a heat sink and you're connected. So that's how a power amplifier looks like. This power amplifier is being modulated. So the stage that would influence the amplitude of the sinusoid is called a modulator. This is an action word. The modulator gets its signal from the microphone, which the microphone converts pressure waves to electric waves. Those electric waves are amplified by a speech amplifier. And the modulator is a large audio frequency amplifier. It has the same power as the power amplifier, because otherwise how could it diminish down to 100% modulation down to nothing? So in a ham radio, the modulator and the power amplifier are the same power. So now you have a 100 watts ham radio, and when you switch to AM, you usually only have 30 watts power. That's because the maker said, I'm not going to put a 100 watt audio amplifier into this radio only for some guy to work AM. I will only use a little 25 watts, 30 watts audio amplifier, and would you please kindly turn your power down to 30 watts to match my audio amplifier. So it's not a technical impossibility, it is just not practical to install a huge several hundred watts audio amplifier in a ham radio. So that was the AM block diagram. On FM transmitter, well, here we go. From the microphone, the speech amplifier would drive the modulator. Now the modulator would intervene in the brackets at the angle, not outside, not in the amplitude. In the angle, it would change the frequency by detuning something. There is a component called the capacitor diode. A diode, when it's reverse biased, it has a small capacitance of 5, 6, or 10 picofarad. Then you apply more and more and more negative bias across your diode. What that does, it would attract the charge toward to the terminals. So the long charge in the semiconductor is pulled apart. And the capacitor is a lump of opposite charge. See, my two hands are two metal plates. This hand is filled with electrons. This hand is robbed from electrons, so it has holes, positive left behind. So the amount of electrons missing from here, they are all over here. So the lump charge gives the capacitance. If my hands are pulled apart, then that's what you do when you have a variable capacitor and you mechanically tune it. But a capacitor diode has no moving parts. Just apply reverse voltage, and that would steer the charge to the extremities of the semiconductor junction and the capacitance could drop. We had one such variable capacitor diode in a resonance circuit, and you can change the frequency by applying voltage in step with the audio intelligence through the modulator. So the AM modulator is a large audio frequency amplifier, and the FM modulator instead is a stage that just applies variable reverse voltage over a diode. The frequency will change, and still you need a frequency multiplier to get up, say, to the 146 megahertz area of the 2 meter band. A power amplifier is always welcome. And for an antenna now I show a Yagi antenna because frequency modulation pretty well is used on VHF and UHF, not so much on HF. So Yagi antennas are there. Now here is an electronic schematic for a frequency multiplier. You feed 1 megahertz to the input of this stage, and this stage is driven so hard that this transistor from the base to the emitter is acting like a diode. It can only take 0.7 volts. Any voltage past 0.7 volts will be clipped. So the wave is distorted. And a distorted wave has harmonic content. So at the output you have a tuned circuit on 2, 3, or 4 megahertz, and in one stage you can obtain a frequency doubling or tripling or even 4 or 5 times. So that's actually the schematic diagram of a frequency multiplier. And we have an oscilloscope, dual channel 1. The input will show one frequency, the output, well, the input is this channel here, the bottom channel, and the output is where you collect the third or second harmonic. So that's what you see for that stage above on your oscilloscope. Now we come to the balance modulator that was mentioned before. This balance modulator is doing a real trick. See how the signal is fed to the primary of the transformer. From the secondary, you may lead 2 wires to this other transformer. Then what comes in from your audio will just go right straight through. But no, here we have 2 diodes and 2 back-connected diodes. And then the carrier wave oscillates. It has positive and negative going out periods. When positive is coming to this point, to the center top, then the top and the bottom diode turn into a dead short circuit. So for the length of the positive going half period, for 1 megahertz, that would be 1/2 of a microsecond. For 1/2 microsecond, a sample of the audio will run through. In the next half microsecond, the carrier reverses polarity. Now it puts a positive here, and those other 2 diodes, they cross the 2 wires. So the audio is sampled in phase, out of phase, in phase, out of phase, in phase, out of phase. And it's sampled millions of times. So if the carrier is at 28 megahertz, then the audio is sampled 28 million times a second. And each sample is alternatingly in phase, out of phase, in phase, out of phase. So this phase change at the output leads to the cancellation of the carrier component, and would therefore only allow the output to have the upper segment and the lower segment. This is called a balanced modulator.
So that's how they get rid of the carrier.
That's how you get rid of the carrier, by balancing it out. So this whole transmitter has a radio frequency oscillator, VFO master oscillator, it's all the same thing. It has a buffer stage, it's not shown there, but it's there. We feed it to the balance modulator, and the speech amplifier has its signal sampled in phase, out of phase, in phase millions and millions of times. Out from the balance modulator come the 2 segments, my 2 rings, 2 segments. The carrier is gone, there's no more. Because the carrier was, I could point one finger up, one down, the 2 canceled each other. So you just have the 2 sidebands. And from those 2 sidebands, now you place a sharp filter, is represented underneath, right over one of the sidebands. So my 2 fingers are the lower sideband and the upper sideband. One finger is in, the passband of the filter, the other finger is outside. So a balanced modulator and a sharp filter eliminates the carrier and one chosen sideband. What comes out is just the sideband of your choice. It may be the upper sideband or the lower sideband. In hand radio equipment, both sidebands are possible, but operators will develop a rule according to which the low bands, they always use lower sideband, and the high bands, they always use upper sideband. There is no law against it. If you want to try 80 meters upper sideband, you may just be lonely there because nobody expects that. But you are not breaking any laws. Just nobody thinks that you would do that, so you will never make a contact that way. Here I want to compare modulation types for you now. This is really important, so read this over again. CW signals. When the transmitter is keyed up, as I'm using my transmitter, I transmit from the keyboard, and I built an interface that each keystroke through that interface, through the computer and the software, would generate Morse code. And often people I have a contact with congratulate me that your Morse code is ever so nice. And then I feel obliged to come back, thank you so much, but my Dell computer is not my hands. I don't want to show off because I'm not a good CW operator, but I made well past 3,000 CW contacts with the help of the keyboard. So, only because you key up your transmitter or your computer keys it up, that would mean that your amplifiers are powered, ready to go, but nothing goes to the antenna. The only time the antenna would see RF, when you actually push the key or the computer is doing it for you. That's the particularity of CW. AM is totally different. You push that key on the microphone, you put your 100 watts into the antenna and it goes forever and ever, just nothing would happen. No one would know what's up. We just say somebody is holding that key, I wish that he could start talking now. So in AM, you push to talk, you transmit something. You actually talk, then you put more power from your audio amplifier into the upper and lower sideband. And then you have everything. Carrier goes, upper sideband, lower sideband, three components they go up. And a numerical example, where you have a small 10 watts transmitter, and when you push to talk, you send 10 watts. When you actually talk, you could put 2.5 watts in either sideband. So altogether, your power increases to 15 watts, of which 10 watts is from your RF carrier in the first place, and with 5 watts, you borrowed audio frequency power and converted it into radio frequency power. That's how AM works. Oh, single sideband is totally wonderful. You only have one sideband, you push to talk, nothing happens, nothing goes, no RF into the antenna. Now you talk, not like this, I'm making a point. I pause between words. Even in between syllables, the RF from the antenna disappears. So single sideband is extremely efficient with the power because it only transmits when you talk. And when you speak up and you talk out loud, then you send the most power. When you speak softly, then you hardly send any power, but you don't hear it. So there's a remedy for this. It's called the voice processor. It's a circuit in your transmitter that reads your voice. You say he's talking too soft. Let me increase gain. Oh, he's talking too loud. Let me reduce the gain. It makes your voice more even. So you have more punch in your voice, but at the end, whoever would listen to your voice, they say, finally, he did do something, I can understand him now, but that's not your true voice. Your voice, the way it sounds, has its ups and downs. So the signal processor alters your voice, but who knows what your voice is in the first place, because you are talking to somebody thousands of kilometers away. All he cares is that he can understand you. So that's a voice processor. It's used in single sideband. FM is different from all this. You push to talk, all available power you ever had, whoosh, it goes to the antenna, whether you talk or not. And if you talk loud or if you talk soft or you don't talk at all, it's always the same power. What happens if you talk real loud, you deviate your carrier up and down a whole 5 kilohertz. If you only talk soft, you only deviate your carrier up and down by 1 kilohertz. So in frequency modulation, you transmit a constant amount of power. The instant you push that key, you transmit something. Therefore, FM is very hard on your amplifiers. And if you use FM for a long wire, you better have a big heat sink and a fan on it, and your fan would kick in more often than in SSB. So SSB is the most gentle mode on your amplifiers, is the most power efficient, it gives you the most range. CW gives you the same range or sometimes even better than SSB, but it's harder on the amplifier. For your M radio transmitter to transmit 10 minutes of Morse code, your electricity bills would be somewhat higher than after 10 minutes of single sideband. Let's put it this way. And the more you pay, the more you use FM, then you pay whether you talk or not. That's the highest power usage mode. See what's coming back with somewhat we have this up. Digital modes. CW sometimes is qualified as a digital mode. From the standpoint of science, CW is a special case of amplitude modulation. It's so far a mode of operation, it could be called a digital mode because all you transmit true and false statement, whether is the key pressed, is the key not pressed. So, and for the operator, it may be a digital mode. For the scientist, is amplitude modulation. Analog modulation uses a sinusoidal carrier which is modulated with your analog intelligence, your very voice. A digital mode is different. In digital mode, you have a radio which was designed and built for the human operator, so therefore it can transmit voice. But now you want to transmit data. So what do? You generate your data. Say you have a whole file in your computer. You dump that file into a device called a modem. A modem would look at each bit, whether the bits are true or false. A true bit is called a mark, and a false bit or zero is a space. Those marks and spaces, they are converted to a different intensity audio tone or a different frequency audio tone. Those audio tones then are channeled into the microphone input of your transmitter. Your transmitter is fake with fake voice. So the transmitter is designed to handle voice. Therefore, all digital modes, they must create something that looks like voice. That's a digital mode. The most widely used ones are the radio teletypewriter as the oldest one, which was replaced by Amtor, which Amtor is just an improved radio teletypewriter with error correction. And then pocket radio is popular. Now we have to go a little bit into data communications, at least for 5 minutes I will press. In data communications, we have synchronous and asynchronous transmissions. You probably heard or know of the American Standard Code for Information Interchange. There is 7-bit and 8-bit ASCII. This code is formatted in such a way that it has a start bit, then it has several significant bits, then it has a stop bit. The significant bits, they start with the least significant bit, and they end with the most significant bit. It could be 7 or 8. 8-bit ASCII is used in your computer when you are running executive files. 7-bit ASCII is created when you check on the keyboard. So we have a start bit. We have 7 bits, you have a stop bit, and then following the stop bit is a parity bit. What a parity bit is an elementary error correction method. Each time you transmit an ASCII character from the keyboard, it consists of ones and zeros. Well, they could be 7 ones or 7 zeros, or 3 ones and 4 zeros. So the number of ones, they could be an odd number, or they could be an even number. That changes each time you press a key. Now the parity bit is a dummy bit that your software artificially sets whether you selected even parity or odd parity. So the software always runs and calls, okay, he has 3 high bits, the rest is all zeros, and he wants even parity. I stuff a 1 in my parity location. Or the next code word, you have 4 high bits and 3 low bits. And the software says, oh, he wants even parity, but 4 is an even number, so I better stuff a 0 in the placeholder of the parity bit. So on a word by word basis, the computer would stuff in a 1 or a 0 to perform the operator selected odd or even parity. Now, Amtor and RTTY, they don't use ASCII. They use a code developed by Émile Baudot, a French telegraph engineer. When we mention his name, we should write Baudot with a capital B. But his name was borrowed and changed to be a measure of the rate at which the information is exchanged. And this rate is called the baud. So the baud, it lose a character from Baudot's name. So therefore it's not his name anymore, and we spell the baud with all lowercase, but we spell Baudot as the Baudot code with a capital B. Now in ham radio practice, there is a device called a terminal node controller. The terminal node controller produces the code. So you can produce the code by packing on a teletypewriter, and each time you press a key, the terminal node controller would set up the Baudot code for you with a 6-bit code, made of ones and zeros. Because you have a terminal node controller, you still need a modem, but often the modem is included in the terminal node controller. Lately, nowadays, the audio frequency oscillations are created in the sound card of your computer, so the sound card is programmed to be a modem. The last time we used a modem was 20 years ago, and we had internet providers that they sent us the internet on a telephone line. So now modems are not being used to log into the internet, and for ham radio digital modes, instead of an outright modem, we use the sound card, and unless you do RTTY and you have an old teletypewriter, or you type on your keyboard, and therefore you create ASCII codes, and those ASCII codes are converted to tones in your sound card. So here is the format of the ASCII code. Here is a start bit, the least significant bit. What else you have? Most significant bit, parity bit, and the stop bit. The stop bit is the level of the idle line, because when you pack the keyboard between 2 keystrokes, you what the press next, so you have a split second there, so the line is held idle. So the idle line is the same level as the level of the stop bit. In data communications, when we had serial ports, they use the plus-minus 12 volt signal, and negative 12 volts was for ones, and positive 12 volts signified zeros. But it is just data communication in the old times of modems. So now in the ham radio, they don't have that. RTTY radio teletypewriter is asynchronous. An asynchronous mode is a number of bits, 6 for Baudot, 7 for ASCII, that they have a start bit and a stop bit associated. So an asynchronous transmission goes by a character basis. Synchronous transmission, which is packet radio, will be a whole long message which does not have a start bit and stop bit, but it has a predetermined number of bits, such as 48. And after those bits elapse, there's a single sync bit. So asynchronous is much faster, and if you are asked, then what you should answer is that a synchronous mode goes by a whole message basis, followed by a sync pulse. And an asynchronous mode goes by a character basis, where each character has a start bit and a stop bit. So that's the difference between them. The packet radio is the typical synchronous ham radio mode, and RPPY and Amateur is the typical asynchronous. Oh, now lately there is a new one called PSK31, which I even tried and had lots of fun with it. Bruce is a master of this mode, and the PSK31 mode is a asynchronous mode. It has start bit and stop bit. Now some data communication theory comes up here. Time is out. I can run over those 2 pages the next day, Thursday, or if you want to stay extra few minutes.
Can we stay?
I think we should stay because we started late.
I'd rather stay.
Okay, let's look into this. What's a binary code? A binary code consists of spaces and marks. In digital electronics, those spaces are called zeros, and those marks are called ones. Digital electronics is based on a mathematical theory, and it's called Boolean algebra. And in Boolean algebra, the zeros are false statements, and the ones are true statements. So a zero, a false, and a space is the same thing, and a one, and a true, and a mark are the same thing. What's a binary code? Well, there only is a 0 and a 1 as those 2 possibilities. 2 possibilities are a binary possibility. So binary code with amplitude shift keying would just change the amplitude of an audio signal. In this example, each false statement diminishes the amplitude to nothing, and each true statement allows the full amplitude to run word into the microphone input of your ham radio. And from there on, your ham radio has no way of knowing whether you talk to the microphone or the sound card, because the ham radio is happy to receive an audio frequency signal that you can process. Binary frequency shift keying is such as when a space is received, the frequency is left alone, and when a mark is received, the frequency is increased. So you see the top line of 0, 1, 0, 1, 1, and on the FSK you see low frequency, high frequency, low, high, high, low, high. So high, there are 2 frequencies, one associated with the zeros, one associated with the ones. There is binary phase shifting, and we'll stand up to point with my fingers here. See how in phase shifting the frequency is all the same, but the signal starts out and ends at a return from a negative going out here. Then it starts out in the negative direction. Over here, it ends up as a return from the positive going direction, and then it restarts in the positive direction. So whether a 0 or a 1 is being sent, let's have a look at 0, 0, 1, 0. Scroll down here to see 0, 0 did do no change to the signal. but then A1 follows a 0, then there is a phase change in this negative direction. And then when that 1 is over, there's a phase change in the positive direction. So binary phase shift T just restarts a packet of audio frequency oscillations going in the positive direction in the first instance or going in the negative direction. Of course, the phase can be shifted many more ways than 2, so then it would just start and stop halfway up the amplitude also. But it's also binary because there are 2. Here we have an illustration of what is 0, 0, 0, 1, 1, 1, 1, 0, and 0, 0, 0 are sent from your keyboard in this succession. Well, the terminal load controller is told to wait until 2 bits come in. And 2 bits could be 0, 0, 0, 1, 1, 0, 1, 1. 4 different groupings of 2 bits. Each different grouping is associated with a signal that starts 0 phase, it starts positive 90 degrees, it starts 0 but in a negative direction, or it starts from negative 90 and so on. So remember the old times in the old Navy, when the sailor would climb up the mast, have a flag, and he'd hold up this flag, and he could hold this flag up this way, that way, or down. So his arm could point in 4 different ways. And a mile over the other ship, somebody learned how to read. That was the significance of those 4 positions. Actually, that sailor withdrew digital communications, because each flag position corresponds to a combination of 2 bits. Because if you only have 1 and 0, then you only have up and down, and that's it. Then you have this side and that side, then your terminal load controller waits for 2 bits and combines them, whether the 2 bits coming in are 0, 0, see here. When the 0, 0 is coming in, the flag is held this way. 0, 1, the flag is up. 0, 1. 1, 1, where is 1, 1? 1, 1, that's the opposite way. So it starts here, and that's the opposite way. 0, 0, and 1, 1. 0, 0, and 1, 1. 0, 0 is a swing from 0 crossing up. 1, 1 is a swing from 0 crossing down. 0, 1, and 1, 0 are opposite to each other. 0, 1 starts from top down. 1, 0 starts from bottom up. They are again 180 degrees opposite. As my 2 arms are 180 away, my 2 arms are again 180 degrees away from each other. So now the terminal load controller can group 2 bits, 3, 4, 5, and in the times of internet connection over telephone lines, they are up to 14 bits. 2 to the 14th power was something like 4,000 or so different possible combinations. Extremely sensitive phase detectors were used. So over there, that phase cross would pretend that the terminal load controller would wait for 3 bits as you type on the keyboard. There's a long string of bits coming, and the terminal load controller would group them. 3 bits are in, next 3, and it changes its phase with 45 degrees increments. And then if there would be 4 bits, then that could be 16 different possibilities. So 360 degrees divided by 16 would be 30 degrees increments, and so on. The higher the number of bits, if the bits are 8, then there would be 256 angular increments, something like 1.8 degrees different between the phase possibilities. So the terminal load controller is doing this. It collects bits that grabs those bits out of your transmission, and in turn would feed an audio frequency signal with such and such phase to the microphone input of the AM radio. And we have come to the last page. In your book, there is the issue of transmit and receive switches. So imagine that you have a ham radio, which is a transmitter and a receiver in one enclosure. When you have a ham radio, you have a transmitter in it, and you have a receiver in it. You could have it in two different boxes, as you may have if you build it yourself. But if you buy it, they put the two into one box. And as they are in one box, they still have an input for the microphone. This is a standard Kenwood microphone from the Kenwood side. That's where I stole this image. But the microphone is feeding your transmitter, and the receiver feeds back into your speaker. So the transmitter and the receiver, they are turned on in turn as you push to talk. When you push to talk, you want to shut down your receiver and you turn on your transmitter. So when you transmit, you obviously want to move the one antenna you have into the transmitter output. But when you receive, you want the antenna to be connected with the receiver. Now, again, if you homebrew and you build your own microwave equipment, you may well build a different separate receiver and a separate transmitter, and a separate power amplifier and a separate low noise amplifier, filters. They are all separate. And then what you have is a relay. It's called a radio frequency relay. This one has N connectors and is rated for a few hundred watts. So the antenna would be connected here, the transmitter there, and the receiver here. When you push to talk, the antenna is switched to the transmitter output. You release the push to talk, the antenna is connected to the input of the receiver. So a transmit-receive switch is by default built inside. There is an actual physical relay or a solid-state relay inside your ham radio that's busy moving the antenna up and down from the transmit output to the receive input. This illustration should not be in your text. You'll never see this test question. The only reason I put it here because it's in your books, and you may or may not be puzzled by it. So in your book, those lines are drawn up in a circle. This is like an exercise for transmission lines. You have a transmission line that is exactly a quarter wavelength long and a quarter wavelength long here. When you apply positive 12 volts through a resistor across this diode, you put a dead short circuit to the ground, you short out your receiver when you want to transmit. Now you have a quarter wavelength line shorted to the ground. The other end is what? Open circuit. And a quarter wavelength line is shorted to the ground. The end of it is an open circuit. So this line section has an open circuit here. This other quarter wavelength section has an open circuit there. So you could cut this off. It's not there. So therefore, your transmitter, the positive would turn on this diode again, so that's short. A diode, when it's turned on, radio frequency currents, they can go backwards and forward through the same block. So this diode allows the transmitter to transmit through the upper arm into the antenna. Now you reverse the polarity, you put negative 12 volts. You put negative 12 volts, both diodes are reverse biased, so they are off. So what's happening when you have both diodes off, then the transmitter is isolated. And in transmission line theory, I'm sure you learned that the other day, that the signal, while it travels down a quarter wavelength section, it will undergo some phase shift. But the phase shift receives itself by odd multiples of a quarter wavelength. So from the antenna, the signal travels 1, 2, 3 odd wavelengths, and it returns in the same phase as the original signal. So the antenna is feeding your receiver on both loops in the same phase. Now, this is a marvelous thing, but it's only good for microwaves and UHF because it's based on quarter wavelength line. So you set it up for the 70 centimeter band, it's no good on 2 meters and so on. So in your actual ham radio, you'll never have this. This is what you have in your ham radio, or one version of it. So I don't know why this appeared in the book, but I was asked last year, and I thought I want to explain this to you. And I still have time, but there is the issue of, this is not from your book. I went to those government sites to actually make justice about how much power are you allowed to transmit. Because they say 250 watts, 560 watts, 190 watts. Who would understand this? So I made up this one diagram and it explains it all. This is a big power supply. And I broke up your ham radio equipment into auxiliary circuits, that's light bulbs, your tuner, and what you have. And a complete transmitter and a receiver, at this power. Then I thought this is a low power transfer. You have an outside amplifier capable of more power. Well, 250 watts DC power, meaning you have a 12 volts radio, you draw 22 amperes from this power supply. 22 times 12 would be 340 watts. 13.8 volts really. So that's how you get 20 amperes, 13.8. You get the 250 watts. So when you read that your licensing permits you 250 watts input, the meaning is that you may draw 250 watts DC power or 20 amperes from a 13.8 power supply. That's all it meant. Now, an amplifier has an efficiency, and the regulation allows that with a basic license, you may output 190 watts of a carrier, meaning that 190 over 250 is 0.75. So the regulation goes around like that, and it merely states that state-of-the-art technology with your solid-state amplifiers, you pretty well have 76% efficiency. So we let you draw 20 amperes DC from the power supply. That would be 250 watts going to your amplifiers, but some of it would go up in heat, and about 490 watts is the most we permit you to actually put into the antenna. Okay, how come that a basic license allows 560 watts peak envelope power? This is easy to explain at the end. Here's this illustration that shows the time domain display of a single sideband signal. As you thought, even between the syllables, the power shoots up, it goes down to nothing. So all it meant that on average, the average of all of those spikes and all of the gaps in between would work out maybe to an even 490 watts. But time by time, when you really speak up, the odd spike is allowed to shoot up to 560 watts. So that is the whole mystery outcome, that a basic ham radio license allows you 250 watts and 490 watts and 560 watts all in the same time. Oh yes, 250 watts is DC power drawn from a 12 volt power supply. 190 watts is based on the possible efficiency of your transistor amplifiers, and the 560 watts is just the highest peak that may last 2 microseconds altogether, and then you shoot 560 watts into your antenna, but then in between the syllables and the words, you transmit nothing. So all that averages out to maybe 100 watts, definitely less than 190 watts. That's it. I appreciate that you did stay the extra time, and then we can start the receivers next time, Thursday. And Thursday, we know each other now, and we know the setup, and we dive right into it right away, all right?
Hopefully without a delay.
Great.
Okay. Thanks, Peter.
You're welcome. I enjoyed this very
Before you go,
much.
Bruce,